So hello guys, welcome to my channel. Today I will teach you about the very famous problem of LeetCode, rotting oranges. It is a very famous problem. I have given many interviews and many of the interviewers have asked this problem. Many just changed the statement but the logic was same and many just copy pasted the question from LeetCode. It's like a favorite problem for interviewers. So yes. Let's just read the problem first, what it is saying, then we will move on to the idea. You are given an m into n grid where each cell have can one of three values. Like we are given a grid like this of m into n size, and every cell of this grid can have three values. First one would be 0, which represents an empty cell like this, and 1 would be a fresh orange like this, and 2 will represent a rotten orange like this, right? Every minute any fresh orange that is 4 directionally adjacent to a rotten orange becomes rotten. Means every cell which is 4 directionally adjacent, like this is the cell and the 4D directionally connected cells for this one are these, and that would be the above one, right? So every minute if there is a rotten orange connected like this, the neighbors will become rotten too. Here you can see, at first this orange was rotten only. At the next step, it made its neighbor oranges rotten also, and then those make the next one rotten, and the next one makes this one rotten, and at the end, all the oranges become the rotten. So you can see a pattern here, like say we are going level by level here, right? So we will discuss about this thing later. First, let's read the edge case. Return the minimum number of minutes that must elapse until no cell has a fresh orange. We have to return minimum number of minutes until there are no fresh oranges. Like in this case, it takes 4 minutes to turn all the oranges of the grid to rotten, right? And if this is impossible, we have to return -1. When it will be impossible, let's look at that case. Suppose there is no edge like this here, there is no orange here, right? And then um, all these are the connected component except this. Why? Because it is not 4 directionally adjacent to other cells, right? So we cannot make it rotten. It would be impossible to make it rotten, so we will return -1, right? That was the whole problem. Now let's look at how it is a graph problem and how we convert it to a graph. So see, we the cells are dependent on its neighbors, right? The answer it depends on neighbor. Whether its neighbors are rotten, then it will become rotten, otherwise not, right? This is why it is a graph problem. I can create a graph like this here for this one. Then we have this, we have graph like this. At first level, this one is rotten. At next level, it makes at the second minute, it makes these oranges this level rotten, and at the next level, at the next minute, it will make these oranges rotten, and then this, then this. That is how it is working in this graph. You can see. this, 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 and this. Right? It is going level by level. It is not like that we are going here, then here, then here. Right? It is just routing it level by level. Right? So yes. Next idea is what approach and why. Why we are using multi-source BFS? We will use multi-source BFS because we have we have multiple sources here. Like it is going level by level. It is not like that there is one source, then it is making next one rotan, then it is making next one rotan. No, it is making multiple oranges rotan at time, and we have to push them all into the queue together. We have to push all the rotan oranges together in the queue. That is why we are using multi-source BFS. Why not be DFS? Because DFS will take us too long. Like we will go this, then this, then this, then it is an empty cell. Then we will backtrack, then come to this, then we have to come here, then here. It will take us so long to make all the oranges rotan. So it's better to use multi-source BFS because we can put all multiple or rotan oranges into the queue together and then make them rotan level by level. The idea. What is the idea and approach for this? What we will be using? So let's say we push. Wait a second. Let me just give numbers to the grid. Let's say we just push 2 and its pair 0, comma 0. This one is rotan. Then we will check for its neighbors. Right? Its neighbors are this one and this one. We will push these two and sorry. Yes. And this. We pushed its neighbor to the queue and make them rotan also. Two, they both will be converted to the 2. And then we pop this one out, push its neighbor and make them rotan. What is neighbor are? 1 comma 1 for this one, right? I can say this is a neighbor for this one too, but we are taking this as neighbor of this one, right? So we push 1 comma 1 comma 1 and then we pop it out and may push its neighbor too, which is right. And we also pop it out, make it rotan and push its neighbor. So it goes on and on like that. Like see, let me tell you with visualization. Here we are going at first from 0 comma 0, then we push all its neighbors, these two, that we make them rotan, then we push their neighbor also and make them rotan, and we push this and this. Okay, that was the idea to make the all the oranges rotan. But how to track minutes? That is the main question, right? So we will track minutes by every time we make some oranges rotan, we will count as plus, right? Every time I visit its neighbor, I will increment the count of minutes. Like here it was 0 minutes, came here and incremented the count as plus 1, then plus 2, and then 3, and then 4 here. So it took us 4 minutes to make all these oranges rotten, right? Now let's come to edge case. What if we can't make all fresh ones to rotten? As I already told you, what if we didn't had a cell like this? We had an empty cell here, and we could not connect this one to this component after these all become rotten. We could not connect this one to this component, and it will never become a rotten one. So in that case, we will return if fresh is not equal to 0. Fresh oranges are not 0. There are some fresh oranges left, and we return -1, right? So that was the idea. All these things we had to handle. Now let's look at the code. Whenever you want to code, just break your code into steps. First, I broke my code into the basic part, like how can I put all the rotten oranges into the queue together. Then, how can I count the number of fresh oranges for my edge case, right? Then I broke my code into the initialization step, like how to track minute. I use distance here to track minutes here. Now fresh oranges variable, which I used below. And then I have one more function to check if the uh, cell is valid or not. Valid means um, it is not out of the bound. Like the grid is not, the cell is not -1, -1. It is not out of the bound, right? And then the main idea of BFS here. So let's look at this. What this code is doing. First, we have taken n comma n for row and call size because it is not given in the input. Then we have this fresh variable as 0 because at the start, uh, until we have not traversed the grid, we have fresh oranges is equals to 0. Then I have resized the grid and distance to perfect size, right? I have initialized the distance values as 0 because at the beginning all the values are 0. Okay. Then I am traversing the whole grid, and whenever I encounter an rotten orange means 2. 2 means a rotten orange here, right? So whenever I am encountering an rotten orange, I push it to the queue. Okay. And initializing its distance as 0 because at the beginning the distance, the minimum minutes, right? Distance means minutes here would be 0. Okay. And I am yes, this is to push I comma j means row comma calls index. Okay. Then I am incrementing the count of fresh oranges because at the end we want to check if fresh oranges are still left or not. Okay, then I am taking answer as BFS function. Then let's look at initialization part. I've used a shortcut of state is equals to pair of in command because I don't want to write this part again and again. So I've used this as a shortcut. You can use this too. Then I have a queue here to push all the rotten oranges and the fresh oranges. Okay. Then here I have declared fresh, and then I've created a distance array to track the minutes. Here the exact minimum time. Distance array is for tracking the minutes of every cell, but minimum time here is to track the time for bestest possible. Okay, at the end, how many minutes it took us, right? So here I am using dx comma dy to traverse the grid. Let's understand this. Let's say I am here at 1 comma 1, and I want to go to this cell. So how can I go? There is a one row less, so it would be 0 comma 1. What did I do? I just decremented the row to minus 1, and right. That's why I have used this. We will traverse all the values to subtract or add from the current cell so that I can go to here. Okay, I hope you are understanding this part. Then we have a function is valid. It is to check if these cells are in the bounds and are not going out of the bounds, right? And if we have not visited the cell yet, this means that we have not visited the cell yet. Why? We have not chosen to make a visited array because visited vector, because we will have to just do some extra stuff for that, and instead of that we can simply just do this part, right? If the distance is 0 for the current cell, that means we have not visited it yet. The minutes are 0 and it is still a fresh orange like this. It's still a 1. 1 means fresh orange and it has minute 0. Then it is a valid and we will make it total, right? What are the prerequisites to make a fresh orange to a rodent? It should be fresh and it should be not visited, right? So yes, else we've written false. Now let's come to the main part of BFS. We are popping first. We pushed all the rodent oranges first, right? Now we are popping one orange at a time and its indices for row and column, and then for that I comma j we are going to its neighbors, like x means I here plus dx of any value of this. Let's say dx of 1 I take, then and I is 1 comma 1. 1 would be 1, so we will go to second row, right? And same with the column. Now we will check if that neighbor is a valid choice or not by calling that function. If it is a valid choice, we increment the minute. Like see, we are here and I am at this node and it has not been visited yet, right? So I check if it's a valid choice or not. I will just make its minute as 1 plus 1 from the last. Let's say we had 2 minutes here to make this orange rotten, and then in the next step would be 2 plus 1. It will take us 3 minutes to make this orange rotten, right? So we will just do plus 1 from the previous value to the new value. And at every step we take the maximum out of time. Why we take maximum out of the time? Because we want the time where the last orange got rotten, not any time of this. At the end, the max will give us the time of last orange gets rotten. And the question may arise for you, why, how we are getting the minimum time? We are getting minimum time because we are using BFS here, because BFS ensures that we visit its closest neighbor first. So obviously it will give us a minimum time out of them all, but we are taking maximum here because we want the time of the last orange gets rotten, right? And then we decrement the count for fresh oranges, because we have just made this fresh orange to the rotten one. Now we will decrement the fresh oranges count and push the row comma call indice of the current cell to the queue so that it can visit its neighbors also. Then at last we check if there are still fresh oranges left. Means fresh are still greater than 0. Then we return -1. That means it is impossible to make all the fresh oranges to the rotten ones. Else we return the minimum time of them all. Okay. So that was the whole idea and whole code for this question. I hope you did understand what I taught you. Now let's look at the time complexity for this. The time complexity for this would be big O and cross n, because we visited every cell once, only once, right? So the worst case scenario of time complexity would be big O and cross n, right? What if all these cells were one, not an empty cell? Then we would have visited every cell once, right? And the space complexity would be big O n cross n. Okay. Why big of n cross m? Because we take this space complexity as the space we use to solve the problem. We used n cross m grid to solve this problem. So yes, the space complexity would be big of n cross m. That's it for the question. I hope you liked it. If you liked it, please subscribe my channel, share it to your friends who also love to solve DSA problems, and like this video. And if you still have any doubts regarding this question, you can ask me in the comments. I will reply. And thank you. We will meet you in the next one. Till then, bye bye.